Well, hi, thank you for checking in here on the BDR lunch gathering videos. We're glad you're here. We want to let you know that we have quite a few of these videos. In fact, if you go to the BDR site and check out our page, you'll find that here under news and lunch gathering, you'll find not only the fact that these educational web seminars are free, there is no cost whatsoever, but you'll find out what's coming up and a complete listing of all the different ones we've had in the recent past and over the past 2 years and a half. All these are good sources of information that I think you'll enjoy. So we invite you to check in, visit with us, and let us know how you appreciate them. There is a little button in the bottom here. It says subscribe. If you click on that to the little bell, you'll get a weekly reminder when new posts are made. And we, again, thank you for being part of our family.
So I'll get started and say hi, everybody. Glad to have you with us. And one of the things I want to start with is by sharing this, which is from our friends at Contronic. If you think Contronic is just phasers, you got another thing coming. They've been going now since 1949, and they produce all sorts of things, including FM combiners, FM coax switches, weatherproof equipment racks, dummy loads that go up to 50 kilowatts. If you need something for AM or FM, they're there, Contronic Labs, and they want to help. They are now run online with their store. So if you want to get some parts, time of day or night, not important, you can order it from them. And it's Contronic Labs. These guys are our friends. And we hope that you'll use them from time to time. So that brings us back now to our guest today, Ray Lewis. Ray wants to talk about co-location. Maybe you've had problems, whether it be LTE complaints from certain cell phone companies, whether it be a competing station, maybe your satellite translator is getting some interference, or maybe you just get up there and your key fob doesn't work anymore when you try to get back in your truck. So Ray, talk to us about this for a while and help us benefit from your experience.
Okay, try to share my screen, Barry. Do you need?
All right, you got it now.
Okay.
There it is.
Okay, I've really enjoyed meeting with you guys for a while. My background was in antenna. I mean, in television at WAGA, and worked there through undergrad and grad school. And you know, you get broadcasting in your blood, you just can't get it out. So I also enjoyed antenna engineering. So I've been doing that for Scientific Atlanta and now Viasat for 40 years this year. And you know, the problem I've had recently is I like to design antennas, but I often get a phone call about 6 o'clock on a Friday evening and from somebody at a remote site putting in one of these antennas. They're trying to do testing, usually G over T testing, and they say we're not passing our test because we have all kind of local carriers that are interfering. And it's the same thing with broadcast. It doesn't matter if it's an STL or satellite downlink. So what I did was I put together, I've probably got more slides than we need. I've got about 60 slides, but everything I could think of to try and mitigate, you know, co-site interference. It's becoming a bigger and bigger problem. I don't particularly enjoy dealing with this. I'd rather be designing antennas, but it's part of the process now. And I mean, I think part of the problem is the received subsystems are getting so good now. We've got low noise amplifiers that have 20 Kelvin noise temperature, and that's something that the radio astronomy guys would have they would have paid $1 million for, you know, 20 years ago using cryo techniques. And now we can go buy this some of the new hemp devices, pretty much off the shelf. And theoretically, it gives you a fantastic, signal to noise ratio. We call it G/T, gain to temperature ratio in the satellite world. But it also makes you a lot more susceptible to the extraneous interference since the noise floor gets so low. So what we're having to do is to bake a lot of mitigation techniques into our antennas. We primarily do auto tracking antennas, mainly for the military, the Space Force, and some foreign. They're usually auto tracking and fairly high end. So it's really important that they have to work. And we really want to do this without a lot of retrofits on site. And we actually do something. We go out to a site about a year in advance, and we do something called a site survey. I'll show some pictures of that, where we actually try to quantify the EMI, the local background radiation. We'll send a technician out, but the problem we've got is we do this, and then it's maybe a year later we get the antenna built and it's being installed, and some other 5G cell sites and things have popped up, and things that we weren't really counting on. So yeah, I just want to go through a few things, looking at spatial discrimination, different antenna types, RF filtering, and using amplifiers that have high compression. And we use some amplifiers that have interstage filtering built into them. And our favorite subject is low passive intermodulation techniques. And we always give that to the new folks, the new engineers, because it can be pretty daunting and pull your hair out. So just kind of wanted to go over these. And this is kind of what I'm hoping to get through, hopefully in about an hour. These are some antennas that we deal with. These are 24-meter class antennas in the upper right. I think a 19-meter and a 24-meter, very high power. Tens of kilowatts of CW power. You can see some of the HPAs on the sidearm here, and we're doing more and more of this for the government folks, and I really enjoy that. I really don't like doing mass market stuff. We like doing the military end of it. And you've probably seen this. I think this is Mount Wilson and all the frequencies we're trying to cram into a particular band. And it's really bad, especially in the Atlanta area right now with the services. Even in the FM band, everyone's trying to shoehorn in translators and sites, and it's really becoming a big problem.
Ray, just to let you know, you're showing us the preview slide too.
Oh, let's see. All right. Yeah, I'm not sure. Yeah, I see that. Okay, I didn't know if that was showing up on. Let's see here. Spell slides. Yeah, I don't know why that is. Let's see. Yeah, I don't know why. I've never seen this do this. Oh, wait a minute. Sorry. Well, I'm not sure how to get this off of here. Sorry about that. I've never seen this happen before. Well, hopefully it's big enough. You can see.
Is there a different window? Do you have a different window where the slideshow is?
Let's see. Sorry about that. Let's see. Oh, maybe this is it. Okay. Let's see. Now what happens? I don't know if that's any better or not, but that's a little, let's see.
Not to worry, but I don't know if.
Ah, shoot. Yeah, I don't know.
Yeah, man.
I've never seen it do that before. Anyway, I'll hopefully it's big enough. But yeah, I'm just talking about the bit error rate, that we have to contend with. Now we've got a lot more data coming down, so it's actually more susceptible to noise. So we've got a lower noise floor, and we've got a lot more data that we're trying to move from place to place. So local interference gets to be a big problem, especially for high data rate. Of course, Shannon's law for bandwidth versus carrier to noise ratio. You guys know all about that, probably a lot more than I do. And some of the problems we've seen is like low noise amplifier overload, and we talked about the G over T degradation because of the T. And I'll actually go into what G over T is and how we can calculate that, because some of the mitigation techniques that we use are really dependent on trying to not degrade this gain to temperature, which is basically a carrier to noise ratio, and what you can get away with, how you do a simple G over T calculation. We do that every day in the satellite world, but it's equally applicable for it's also applicable for any type of studio transmitter link, for instance. And here's something I've had to go to the other side of the world for several times. We get a problem, and if you get broken or fractured coax shields, if you've got coax going from a high power amplifier and your diplexer, your frequency diplexer is actually located in the feed, and you get any type of break in the coax in the shield, this can act like an antenna. Almost remember the Helix that they used to sell for tunnels that used to have the slits in them. Well, if this starts to radiate, the game's over, because this SSPA actually puts out white noise, and once you radiate it, that's really no way of keeping that from getting into the antenna. So this is something to really worry about. Make sure you've got good strain relief in this. We'll talk about this in a little bit later, but we got some natural sources of RFI. We got, of course, we got solar noise. When you're familiar with the solar outages, water vapor, and terrain. A lot of these big antennas, I'll see in the next slide, they're actually located in valleys so that they can act as a natural barrier to terrestrial interference. So, in fact, you can see that here. This is a site in Canberra, Australia. This is the big Deep Space Network 70-meter antenna right here, the biggest antenna. And then the next antenna over is one I designed several years ago. It's a 10-meter TT&C station, and you can see this Canberra site surrounded by mountains all the way around, and they've got masers for the low noise amplifiers. It's everything's cryo cooled. Money is basically no object, because this is what they use for the deep space probes. So we have several different types of potential interference, ranging from the terrestrial sites to other satellites, and of course the sun raises the antenna noise temperature. Anything that raises the antenna noise temperature is a consideration. And you've got other uplinks. You can see the 70-meter right here. They've got other uplinks that we have to really worry about, because any high power amplifier is going to have a white noise component to it that can potentially raise the received subsystem temperature above the Boltzmann's constant. We'll talk about that in a few minutes. But one of the biggest problems too is also strong signals. Even though they're out of band, they can get into the received subsystem, the low noise amplifier, the receiver, the post amplifiers, and basically create a saturation situation. And a lot of the QPSK signals, they like to operate in a linear mode. So this is something we have to really watch, even if it's not noise in the receive subsystem band. There's really two things to consider. You've got the low noise amplifier compression, the amplifier compression, and then also the white noise generated from all these radiators. And both of these have to be below a certain level to not degrade the G over T or the carrier to noise ratio. And I'm pretty sure you're familiar with the geosynchronous arc. We're using satellites with the same frequency band, frequency reuse, and we use spatial separation of the antenna. And right now we have an angular separation of only about 2 degrees. So the antenna, the Earth station antenna, has to have a fairly good side lobe envelope, because any energy you pick up off the main beam out to 2 degrees, shows up as interference too. So it's kind of interesting now when you're trying to use the satellite geosynchronous arc. We used to be noise limited, but it's actually interference limited now. So we get tasked with having to make antennas that have low side lobes, a lot of rejection from once you get off the main beam, and there's always a trade-off between that and the gain of the antenna. So it's kind of a problem between the two. I was actually doing that this morning. Here's just some of the domestic GSM frequencies. One of the ones that's most problematic is right up here around 1.9 gigahertz. We have a cell site just across the street where we do a lot of our testing, and I think they're putting out 20 or 30 watts right across the street at these GSM frequencies right around 2 gigahertz. It's a big scourge. And yeah, here's some terrestrial sites versus satellite sites, and a lot of times with satellite links, we sometimes have a carrier to noise ratio of only about 10 dB, and terrestrial links, which, by the way, we used to make terrestrial antennas. We made all the you're probably familiar with cable wave. Scientific Atlanta used to make the terrestrial antennas, and Cable Wave bought that, and that's how we got started in the satellite market. That's been back in the late 60s, early 70s. That's been an awful long time ago. So we have some experience doing the terrestrial antennas. These are actually pretty good antennas. These are actually cavity-backed paraboloids, so they actually have a pretty good front-to-back ratio. I've got a few slides of those. And I think everybody's real familiar with ComSearch, and actually the FCC website is quite good also. I'll bring that up. You can put in your latitude and longitude, and you can find all the licensed keyword there is licensed sources around a given location. So I always try to do that and see what's supposed to be there. So I know you guys use that a lot. But I'm very been impressed with the FCC website too. I've had pretty good luck with that. Let's talk about antenna noise temperature. A lot of folks don't know what that is, but every antenna, okay, sorry about that. Okay, sorry about that. That's what happens when you have 500 years of experience on here. So I like that. So that's what I like about you guys. There's not many questions you guys can't answer. So I like that. Okay, let's see. I was talking about antenna noise temperature right here. Every antenna has a noise temperature, and that's just a power of what the antenna sees. You can point it at the hot earth, and the hot earth looks about 290 Kelvin. And as you start to raise the beam above the hot earth, it gets less and less. And this chart on the right, a friend of mine did this many years ago, Jim Cook, and it gives a pretty good indication of the antenna noise temperature as you start to lift the antenna off the ground, which is 0 degrees, all the way up to about 30 degrees versus frequency. This is 100 megahertz. You can see when you get down to 100 megahertz, it really doesn't matter a whole lot. As you start getting in the microwave band, you can see for 30 degrees, see we're down here around 25, 30 Kelvin. So you can get some really good system noise temperatures by a directive antenna at microwave frequencies. And let's see. Yeah, just to give you an idea of G over T, I don't know if you guys have done G over T calculations very much, but this is something we do every day. Basically, you have an antenna, and this is a G over T is a receive system figure of merit. So this is probably the most important receive calculation we have to do. And this is a pretty simple view right here. That can get pretty complicated, but basically you have an antenna with a certain gain noise temperature at a given elevation angle. This is 5 degrees. Then you have some losses between the antenna terminals and the low noise amplifier input. And then you have some losses after that going to the receiver. And the way you calculate this is you calculate the gain at a given point, pick a reference point. Usually we pick the input of the LNA. It can be anywhere, but the gain and the temperature reference point have to be at the same point. So you calculate the gain. In this case, we got 32 dBi minus 1 dB of loss. That's about 31 dBi of gain at this point. Then you calculate the received subsystem temperature. So it would be this 60 Kelvin that we've got for the antenna. Again, from that previous chart, that's a really good estimation. And that power actually gets reduced by this 1 dB of loss right here. So that's actually a reduction in power of about 1.25. So you divide the 60 by 1.25, and then you have to add this 1 dB of loss right here. 290 is, that's pretty much room ambient in Kelvin. And that gives you the temperature in Kelvin of this 1 dB loss right here. And then you add this LNA. It's kind of an old example, but it's 120 Kelvin. And the good thing is, see, once you get past the LNA with 40 dB of gain, you get to divide all of the contributors after that by a factor of 10,000. So what that means is that everything before the input of the LNA and the LNA itself is really important for the receive subsystem performance. So what you want to do is you want to have minimal losses. It's almost a factor of 2 to 1. For every half a dB of loss, for instance, that you have before the LNA, that hurts the G over T by 2 because you have a decrease in antenna gain, and then you also have a increase in the system noise temperature. So a friend of mine says it hits you in the front and it hits you in the back. So that's why we do everything we can to try and minimize this loss up here. So that's just really important as a precursor, because some of the mitigation techniques we use, we really need to keep this in mind, because you don't want to do anything that really hurts this receive subsystem any more than you have to. And we've got all kind of formal spreadsheets that we use for this. This is just some examples. They actually get quite a bit more complicated than that. So this is pretty much automated. We'll always have a required G over T ratio. And of all the customer requirements, this is usually one of the best, one of the most important. We also have to include the transmit subsystem temperature too, because each HPA has a certain noise power in the receive band. This was 125 dBW per hertz, and then we have some sort of isolation following that, a filter, diplexer. And this is when I was getting back to the cable. If you have any kind of breakage or RF leakage in this section right here, it leaks out and it gets back into the antenna, and there's really nothing you can do. So cable leakage is a big deal with this. So that's put a lot of people on airplanes in the past. This shows you, we're talking about cable leakage. We were talking about that. It really has to be good, because like I said, these LNAs they're 20 Kelvin, 25 Kelvin now. This is uncooled. So to get down to a noise degradation of 1 or 2 Kelvin, you've got to have a thermal noise power down here on the right of about a minus 226 dBW per hertz, which is really small. So if your high power amplifier has a output power of minus 160 dBW, you're gonna have to follow that up with a diplexer of say 70 dB, and 160 dBW per hertz is really quite good. You have to follow that up with another 70 dB just to get down in this 230 Kelvin, which that'll only give you about 1 Kelvin system noise temperature increase. So it's really important that you mitigate the white noise coming out of the high power amplifier, solid state power amplifier. And again, everything has to be really RF tight from the SSPA till you get to the diplex or the filter at this point right here. So that's really important. This is some pre-LNA filters. This is not a thing to go cheap on right here. We use several vendors, but I guess our favorite is a company called Microtronics, and they can do some pretty miraculous things with coaxial filters. This is one right here that has it's got a bandpass of 2.2 to 2.3, and when you get down to 2140, it's all the way down to 60 dB rejection and 60 megahertz above the bandpass. We're already at 60 dB rejection, and you only have a half a dB of insertion loss here too. So trying to find a really good LNA vendor is a big thing. You can see it, see the pre-LNA filter right here, and it loops over to the low noise amplifier. And I'd like to talk about these amplifiers. They're fairly high-end amplifiers that we use too. They have interstage filtering to help with the noise mitigation also. And speaking of amplifiers, here's a couple of considerations. We're going to really get into compression level. Like I said, there's 2 things to worry about. You got noise temperature, and then you've also got to worry about compression. Because if you compress things, and you've got most of the modern, digital signals, they don't like to be anywhere near compression. They usually try to keep 10 dB below compression. But Here's an amplifier that we use. It's from, but you can see that the difference in the 1 dB compression point, output compression, see it's plus 4 dBm right here. Here's another one from a company that we use called Amplitech that has a 1 dB compression point of, I think it was, let's see, the output compression, I think it's plus 20 dBm. Yes, plus 20 dBm. So you got a 16 dB delta in compression, which is really huge. So in other words, you can tolerate a lot more extraneous signal level coming into this unit on the left versus the one on the right. Now the downside is the cost is probably I don't know, 40%, 30-40% more. But one thing I've learned is you don't want to go cheap on the low noise amplifier or the filtering. Anything before the especially before the preamplifier is not a good thing to go cheap on. And also, this is a fairly new device. It's got 35 Kelvin noise temperature up at KU band, which is really phenomenal. You can see the noise, that's a half a dB, and you can see the noise temperature of the one on the right is 0.7 to 0.9 typical. So it's pretty. You get better performance, you get better compression. So this is a good thing. You can have a lot more extraneous signals coming into this before you wind up, being compressed. And speaking of amplifiers, especially down at S-band, we use a company in Texas, and they're really good about making these amplifiers, and they put RF filtering in between the sections. In other words, what you can do, because you don't want a lot of loss before the LNA, what you can do is have a small amount of gain, maybe 10-15 dB after the first section, then go into a filter, and then have the rest of the gain after that. So that way you kind of get the best of both worlds. You can get good noise temperature, the 30 Kelvin noise temperature, and you get phenomenal compression. This one has a input compression. You can put up minus 30 dBm in these transmit uplink bands, minus 30 dBm into this, and that's at the compression level. So that really helps. That also reduces the amount of diplexer rejection we need, which helps with the G over T, because the diplexer doesn't have to have as many poles. So the insertion loss can be, quite a bit less too. So that's again, not these aren't cheap, but again, I've found that anything from the amplifier forward is not a place to try and save money if you can. When you get past the preamplifier, there's a lot of what I call post amplifiers. If you need to do some more amplification, mini circuits, they have some. They're up to half a watt amplifiers, and they're actually pretty reasonably priced. They're a few $100s. So they have good noise temperatures of about 5-6 dB, 4-5-6 dB, and like I said, you can go up to a compression of close to half a watt with these things. So you're really not going to compress anything. So I like to use these again with another filter in front of it. If my philosophy is filter early and filter often. So what you want to do is you have a good filter after the LNA, before this post amplifier, and that helps mitigate the extraneous signals also. Okay, like to get into some of the site interference assessment. Like I said, we send somebody up for a site assessment about a year before the system goes in, and they take some pretty common tools. We've got some dual ridge test horns up here in the upper right. These things cover 1 to 18 gigahertz, and actually, there's a guy on the internet. Some of you, Kent Breton, he makes these little PWB antennas. They're actually quite good. They're $10, $15, $20, $30, and this is pretty good for low frequency, 400 megahertz to 1 gigahertz. And then I've got a disco, and sometimes we'll use that. But we'll take a Philfox spectrum analyzer out there, and we typically have some good low noise amplifiers. Of course, some of the newer Philfoxes have LNAs built into them, and they'll dwell on a particular location for maybe 15-20 minutes, and then move it 20-30 degrees and dwell and do a capture. The idea is to try to capture all the signals at that point in time. Now potentially somebody could not be transmitting and you won't capture it, but that's really about all you can do. That's one thing you can do is if you want to set this up with a disc cone, for instance, you can leave that on overnight, capture all the signals. But it's really important more and more to do these site assessments before you start, because once you put the once you deploy the receive subsystem, it's a lot harder to go back and try and retrofit and install filters and try and figure out what's going on. And so this was done in Duluth, Georgia, I guess last year, and this is with one of these. This is just a raw background with one of these antennas. So we got signals up to about minus 28 dBm with just a super low gain antenna. So you can see we have a lot of interference, especially from 800 megahertz to 3 gigahertz. So you've got a lot of interference to contend with. And one thing you've got to think about too is you got all these signals coming in, and if you don't do something to mitigate this, they all can add up. It's just like a multiple carrier going into a high power amplifier. You know, the amplifier, if you've got two carriers, you really can only put in about 50% of the output power before you reach saturation. So, you know, it's really the composite power of all these signals can be more than what you think. And we've got minus 28 in this lower carrier, I guess, in the 900 megahertz band, but it's really the composite of all of these. And I'll show a couple of just sample spreadsheets that will just give you some indication. So anyway, this is just some more data that we've taken as just an example, spectrum response. And again, cell carriers are some of the biggest problems. And I know that they're talking, they're giving us a hard time with broadcasting now, worrying, you know, if we have, I think the 5th or 6th harmonic can actually get into some of their equipment now too. And used to be last in with the FCC, and you had to accept the noise, but I don't think that's necessarily the case anymore. You guys could tell me a lot more about that than I could. There's just another measured background, and this one is basically the same plot, but I've normalized it to isotropic, and I'll show you how you can do that. You just take the gain of the test antenna and subtract out any low noise amplifier test LNAs. And you really want to normalize this to see, you know, what the absolute signal level is into an isotropic radiator, because that's a lot easier to work with. Then you can take that and look at that in your new antenna to see what kind of spatial mitigation you might have. And this is the same thing. It's just kind of a time lapse. If you leave the spectrum analyzer just taking data and you look at it versus time, you can get a kind of a scatter plot, and that's pretty useful too, because like I said, you want to take get the technician to take a good book and sit out there and, you know, take a lot of data. And this is just a sample that they actually fill out on site. Now they also recapture the data digitally also too. So we'll have a good CSV file that goes with this. But you can see in this case, the receive antenna gain is about 10 dBi for this case, and the LNA, this is the test LNA now. This is a little test antenna that they take out along with a little low noise amplifier. It had about 34 dB gain. So what they'll do is they'll correct for any interconnecting losses, and, you know, translate this into an absolute power level into a, you know, isotropic radiator, because that's a lot easier to work with. We want to make sure we do this because they get back to Atlanta and you know, you don't have it normalized to isotropic levels, and there's always a question of, you know, is this data good or bad, or what it is. So yeah, here's this is actually at one of our locations in Atlanta, and we've got a cell tower actually across the street. I think it's putting out about 20 watts or so, and I've got a space loss of about 82 dB. And but these antennas can, this is a 7 meter at 2 gigahertz. It has about 42 dB of gain, but we are somewhat in the near field of this. If it's 500, 1,000 foot, these satellite antennas really have a they have a good they have a nice tight pattern, but when you get in the near field, it broadens up. I'll show an example of that. And this is just a quick overload budget for this particular site. I guess it's about 10 watts that they have. It's about 500 feet away. So you can see that with our pre-LNA filter rejection of 80 dB, we're actually not doing too bad. We're well below the compression level. If we weren't using this 80 dB pre-LNA filter rejection, that we would be in trouble. So it's important, even at 500 feet, and that gives us about 82 dB of projection, but 10 watts is about 40 dBm coming off of this cell tower. So this is pretty simple. Well, let's see. And here's another compression budget that we did here. This is from the uplink leakage that we were talking about. We had about this is about 500 watts, and the diplexer has a rejection of almost 100 dB, which is pretty healthy. And we go through the receive chain at about minus 37 dBm if you go through everything. Again, this is using one of the LNAs that has a interstage filter, so it's got a compression limit of about minus 30 dBm. So that's a high-end LNA. Even with that, we've only got about 7 dB margin at the receive input down here. You can see that. So you can see that, when you start transmitting 500 watts, 1,000 watts, you need a fair amount of rejection. And here's just another antenna plot here for, we usually take these for every 20 degrees or so. And time's getting away from us, but here's just some more plots. Sometimes we can't put in filtering. We actually do some systems that are wideband surveillance systems, so you really can't put in filtering. And what I've had to do is actually, we have a potential of blowing out the LNA if we have, due to the local interference. And there are devices that you can get that are basically pin diodes, and what they'll do is they'll start shorting out the input after a certain level. And that's this device on the upper right. And you need to look at, again, this bottom. This shows the level across this band, 1.8 to 9.8 gigahertz. So you want to look at this composite power. See, we have a composite power of 19.7 dBm in the red, with a maximum overload to this LNA without damage. This is a damage level is 15 dBm. So we have without this limiter, we have a potential of just destroying the LNA, and that, unfortunately, this has happened before. Site remediation techniques. Again, we talked about antennas. I spend most of my day, doing reflector antenna design, and it depends on the illumination, the feed subsystem. There's a trade-off between the gain and the side lobe level. Again, these side lobes that you can see, the lower they are, the better they are at rejecting other interfering sources. And usually, if we have a higher side lobe allowance, I can get more gain. So there's kind of a trade-off between the two. And I think we saw that. That's the geosynchronous arc. We have a lot of requirements. It kind of reminds me of our FCC, spur mask that we have to deal with. We have something similar for a lot of these satellite antennas. I have FCC and some international regulations that we have to stay below a certain mask to operate in the geosynchronous arc, because they're not necessarily interested in the receive interference as much as they are in the transmit. But if we've got an antenna that has high side lobes, we can actually start interfering with other geosynchronous satellites in the arc at the same time. So this is pretty highly regulated. We have to go through a acceptance with the FCC before we can certify a lot of these antennas. I wanted to talk about this just a little bit. This is again in spatial discrimination. If you get close, like the antenna across the street, or with the interference, you think you're getting a lot of spatial discrimination. You can see that in the top left, that's a measured secondary pattern at 1.85 gigahertz. The bottom right is what happens if you get 100 meters away, 300 feet away. And the scales are different there, but you can see it spreads out. The pattern is no longer monotonic. It kind of has a null, and it spreads out because that's the near field pattern of the antenna. So you don't get as much spatial discrimination for close in radiators as you might think. And I guess that bottom left is one I'm pretty proud of. This is kind of what you can do if you really work hard on having a low side lobe level for a given application. You can see past the first side lobe, but we're down 45 dB on that. So that's kind of a good example of what you can do, and that's really just controlling blockage, and it's controlling the feed illumination across the reflector, and also having, to some extent, having a good reflector surface. I'm sure you're probably familiar with the shrouded antennas. I know we use a lot of grid pack antennas for STL, but these shrouded parabolic reflectors are actually quite good. Like I said, we used to make these before it was sold to Cable Wave. The red curve on the right is this antenna. It's pretty small in terms of wavelengths. A standard STL antenna is only like 7 or 8 wavelengths across one of these 4-foot apertures. It's at 950 megahertz, but you can see you have a pretty high side lobe envelope. And if you can put a shroud around that, it drops down into the black. So it gives you a lot of spatial discrimination with that. So the shrouded reflectors are actually quite good, and also allows you to put a radome over the front of it too. So you can see the shroud has a good effect, and I've used these for different applications. I've also designed them for our to mitigate multipath on instrumentation antennas. And I don't know if you've seen this or not. This is we used to use these cornucopia antennas. I put these in here because they're quite good. They're some people call them tunnel antennas, and I guess a lot of them were used horsehair absorber because they were pointing at the ground. So antenna noise temperature is not as much of a concern since they're pointing at the ground anyway. But they have incredible front to back ratio, and it's basically a soft set reflector. Some people call them hoghorn antennas. We've done this from time to time, but that's kind of one of the best cases of antennas with low side lobes. You can do the same thing with horn type antennas. If you put absorber around the horn, just anything. But again, you have to be a little bit worried about what you're pointing at. You wouldn't really want to use this for a space application because that absorber looks like 290 Kelvin. It'll raise the antenna noise temperature really a lot and reduce the G over T. So I've seen young engineers actually try to fix problems with absorber and get into a lot of trouble with the G over T. And these are some of the antennas we're most familiar with, the mesh type grid antennas. So actually they're only like 4 or 5 wavelengths at 900 megahertz. So to be honest, there's not a lot you can do to control the illumination pattern, but they're not going to have a great side lobe performance. They're fairly inexpensive, but as far as mitigation from other interferers, they're not that great. One of the other antennas that we've shown would be a lot better. I guess one of the worst case too, you probably remember the old fly swatter antennas. They're not used by the FCC, not allowed by the FCC anymore, but it was great because you could put everything on the ground, easy access to everything, and you just put a flat plate up at the top and use that. But the scattering is pretty atrocious off of the top of this thing too. So, but that's probably one of the worst cases that we have. Here's this is our antenna range. It's about 30 miles from where I'm at right now in Duluth, and a lot of our antennas we have to validate these side lobe envelopes, the gain, and the polarization characteristics. So we're going to be going up there in a couple of weeks with another antenna. I kind of like it. It's out in the middle of nowhere, and you can see a radiation pattern on the console there being taken. It's actually a 3-axis positioner, so we can roll it, change the elevation and azimuth, and take antenna cuts across all these axes. So there's another tower about 1,500 feet away that is fully motorized and controllable, and we can change the frequency and the squint of the dish on the other side. I want to just briefly touch on passive intermodulation. We deal with passive intermod quite a bit here also. I know it's been a problem with sites that have multiple FM transmitters, high power signals, and I'm sure you guys have dealt with this probably as much as I have or more, but we deal with this a lot. It's really in the satellite it's really a problem up at X band because the transmit and the receive bands are so close together. And if we're transmitting more than one carrier, you can actually generate intermodulation products that are approximately the same signal strength of what you're trying to receive. So that's a real problem. And this I touched on. I've heard people talk about it, that the FCC requirements. I guess they only required about -80 dBc harmonic rejection. So that can be not enough for what we're seeing with some of the cell carriers now. I think we're actually talking about the 7th through 9th harmonic. I know there's some good papers on this. Jeremy Ruck, I think he may be on here actually. He had a good article in Radio World about this in 2017. So it's a big problem, but you've got to have at least two high power carriers. If you have more than two, it even gets worse. You can imagine on Mount Wilson. And we actually have a PIM lab where we actually test this, and we have experience with this. Some of the metal to metal interfaces, they're actually lapped. We have people that actually hand lap these things, have a lapping machine, and they'll actually make these, put a mirror finish on it, because any gap between the metal to metal contact can make a micro arcing potential. And anything that has a potential, if it has a diode characteristics, like two different types of metal or non-contiguous pieces of metal, that's enough to set off PIM. And again, a lot of times we're looking down -130, 40. I've even had one like 155 dB below the carrier. So these are pretty phenomenal requirements that we have to contend with. And like I said, we like to give this to the new guys because it's as much experimental effort sometimes as it is anything else. And you have a program manager wanting to know when you're going to be done, and usually it's something like a metal shaving, or I think I had a chart next. We had a problem with the mechanics actually using never sees on some of the stainless steel fasteners in the reflector, and that has metal particles in it. That was enough to create an intermodulation issue. And just, one way you can tell with intermod, it's just like with the old spectrum analyzer. You probably remember that if you vary the signal strength, you get a lot more variation with the intermodulation signal than you do with a fundamental carrier. It's not a 1-to-1 relationship. It's more like 1 to 3. So anyway, I'm sure you guys are very familiar with this too. Yeah, and this is just an example right here of two carriers. Say this is 8 and 8.3 gigahertz, two high power carriers, and we'll generate intermodulation products down here around 7.7, 7.4. And usually it's the third order that get to be the biggest problem for us. If you start dropping down it, you can see as you get further and further away from the uplink carriers, they get to be less and less of a problem, but they are there. And if the receive subsystem is close to the uplink band, that it can actually mask and certainly degrade the downlink signal. So here's just another example right here. Is a satellite that's downlinking around 7.75 gigahertz and got two uplink signals, and you can see the third order product of this is right at the downlink signal. And if you don't, it looks like in this case it's approximately the same level. So that's going to create a lot of problems with the bit error rate. And so we go to a lot of extremes to try and mitigate this. We'll actually electroform. We'll take a lot of the components and we'll make electroform components and just make one component that's doesn't have any seams or braces. And there's actually some special waveguide flanges that you can use to help with this too. So this is a pretty big deal. It's not cheap though. So anyway, you can get the same kind of thing. This is basically a testing site. You have two transmitters and have a receive subsystem. I'll probably show some. I think I've got a couple of slides of when we're doing this. Basically the third order is the one that you have to worry about the most. That's 2 times either one of the carriers minus the second carrier. That's going to be the one that's closest in it. And usually it's the one that's the most problematic. And I was just looking at this. If two FM stations have the potential of 56 intermodulation combinations, if you go all the way up to 7th order. So I know some of the cell sites have been I think they're, 6th and 7th order. They're way on up there like that. I guess it's a odd combination. If you get 3 FM stations, they got almost 300 different combinations of potential frequencies. So it gets to be more and more of a problem as you get on a site with a lot of interfering, a lot of FM stations, for instance. And we do a lot of testing in our backyard, right behind my back, actually. So we have this is 2 1,000 watt amplifiers, and we feed that in, and then we look at the third order in the spectrum analyzer, and we've got some specialized equipment to do this. So this is something we take pretty seriously, and we're trying to measure things down to like minus 165 dBm. So there's a lot of time and money actually spent on passive intermodulation. And again, there's several papers on this. You've probably seen a lot of them, but again, anything that can create a diode junction is a big problem. So you want to keep anything that looks like a diode junction out of the view of high power if you can. Here's one of our engineers actually doing some high power testing here with 2,000 watt transmitters. And anyway, again, it's just 2 signal generators that goes into a special diplexer, and they take the output of that going out to the device under test. It has to be pretty pure to start with. You want to make sure you don't have any issues going out. Here's some test sets. We will validate the feed subsystem first before it's actually put in the antenna. And I wanted to mention this too. We also have issues with what we call passive harmonics. It's very similar, but a lot of the missile destruct systems, they'll uplink at 400 megahertz and receive at 2 gigahertz. So you can actually be on the 5th harmonic. So it's the same kind of deal with that. We take the same precautions because they have to operate at the same time. You're just trying to mitigate the 5th harmonic with that. Here's a couple of interference scenarios that we've had. No time's getting a little bit light, but this is one out on the West Coast we had recently, and there's some of the sample data, and there's some of the composite data that we had. We calculate the composite power is almost up to 20 dBm at this point. Maximum overload to the LNA is 15 dBm. So we had about a minus 5 dB issue on this particular system. And what we did was we came up with we had to install a new filter. We got our folks at Microtronics. We needed to pass the low frequency and the high frequency, but we needed to mitigate all this stuff from 1.9 to 2.1 gigahertz. So you can see they designed this filter that actually has really good rejection in this band with a really low insertion loss in the pass band. I think it was only about half a dB. There's some really good filter vendors out there. They're not necessarily the cheapest, but they're not terrible. I think this is a few $100s for this kind of filter. But let's see. Here's another subsystem here. This is a kilowatt system on the right, kilowatt diplexer, and you can see the little mini circuits post amplifier there on the left. And I actually put another filter. This is a company in Canada called DCI. They make some fairly reasonably priced filters that you can buy, because performance, again, once you get past the LNA, is not that important really. But what is important is to have a amplifier that has a good compression. This thing's got almost over half a watt compression, so probably not going to compress it. And then I go through another filter before you get into this post amplifier. So again, filter early, filter often. So like to every application stage, I like to change that out. Here's one that just happened. We had some interference issues, and they'd use some off-the-shelf filters from mini circuits, which they make good stuff. But if you get a higher end filter, there's the difference in the roll-off between the high end filter and the mini circuits filter there. So you can see that we had to take out these blue filters and put in the new filters from Microtronics, and you can see we got really pretty phenomenal drop off. But and the price, I guess, difference isn't that much. It's going to be a few $100s more, but you can see the performance is actually quite good versus what you can get off the shelf. We've also used diffraction fences too. This is one of our earth stations that, believe it or not, we had to protect a TV station that I used to work for, and they had a ENG repeater, and they're the same band. So we had to put up this diffraction fence. We modeled a diffraction fence and to basically shield everything in the direction of the ENG repeater. So people thought we were putting in a drive-in theater when we put this in, but actually worked out fine. It's been in operation, I guess, 4 or 5 years now. So sometimes you have to do things like this to try to help with the mitigation too. It's called a diffraction fence. And let's see, I guess this is about it. Just I guess the takeaway is, use robust filtering. They're not always the cheapest, and use high compression, low noise amplifiers, and that's a big deal. And it's also important to get a good assessment of the actual frequencies, the EIRP, and the location of the everything around you. And we used to do it a year in advance, and we're finding that we have to do it, maybe a year in advance, and then maybe 6 months or 3 months, and before it ships out. Because what you don't want to do is get on site and have an issue, which unfortunately does happen. And anyway, you got to protect the LNA from overload, and especially if you've got any kind of uplink transmit in a duplex situation. Anyway, just keep in mind that any near field effects of an antenna, if you get within it's about 2D squared over land, but 2 times the diameter of the antenna squared over the wavelength. That's considered far field. If you get within that, you'll start broadening up that secondary pattern. So even though you think your earth station antenna has a lot of spatial discrimination, if you get a interfering station that's a few hundred feet away, it's not going to be what you think it is. And again, passive intermodulation is something you want to give to the new guy, because they're difficult to troubleshoot, and it's a lot of empirical work. I mean, you take all the precautions you can, but anything that can act as a diode source is a big deal. That's about all I have. I think we just about hit the time. So we're glad to talk about what I know, but like I said, we've got an awful lot of experience here that we can talk about. So
couple of
questions.
questions.
With you guys. So.
I just wanted to clarify, I think I figured it out, but when you speak of a high compression amplifier, you're actually speaking of the threshold where it starts to compress. Is that correct?
Oh, that's right. Yeah, that's exactly
when you talk
it.
When you say high compression to a broadcasters, we have it exactly backwards. So it confused me a little bit.
Okay. Yeah. How much power can you put into it and it still maintain a linear output? So, and the problem is if you start compressing all these QPSK modulation formats, a lot of them, they don't like that. So it starts giving you a lot of bit error rates. And so it's a pretty big deal. And unfortunately, we're seeing this more and more.
So you're working with very high frequencies and very low noise levels, and I'm glad somebody knows how to do that, because I sure don't. The fly swatter antenna reminds me of passive reflectors I've seen. My wife pointed out what appeared to be a billboard on a mountaintop. Said, why would anybody put a billboard up there? And of course, it was a microwave passive reflector, I think, from old phone company microwave.
Yeah, I've seen pictures of those. I've never seen one in reality. Wow, that's pretty big. I tell you what, these Hawkhorn antennas, cornucopia antennas, I've heard people say that the AT&T, they would actually transmit and receive on the same frequencies without setting up an oscillation. I don't know if that's true or not, but they said they could do that because of the extreme front to back ratio. I asked a AT&T employee about that one time, and he said he thought that was right, but I don't think he knew a lot about it. But they do have they do have 90 dB front to back ratio. So
saw an awful lot of those at phone company microwave sites.
Channel 28 in there, back when they were at their old original site, was not line of sight to Mount Wilson, so they hung a passive reflector on Children's Hospital across the way, and they bounced their STL off that to get to Mount Wilson. So that was in use for many, many years here.
Ray, when we had this change in the C-band, with it being given away to 5G, has this created problems that you've dealt with?
Yeah, I'd say it has. We got people over in England right now that are fighting this, and like I said, it's just so hard. I mean, we do a proper site survey, we try to do everything we can, and then by the time we get the thing built a year later, things have changed, and it's like beating your head on the wall. I don't really enjoy doing this and that much, and I know it's frustrating for everybody, but you almost need to continually do a site survey like every 2 or 3 months, almost, the way people are putting up things. And also the received subsystem temperatures are getting better and better. We're getting better and better G over T. I can give you a really good G over T, but it's because the T is going down, and that makes it more susceptible. I mean, these are radio astronomy things. The radio astronomy people 20, 30 years ago, they would have put everything in a deep canyon trying to mitigate and there wasn't as much, interference to contend with anyway. I know the radio astronomy people are really having a problem right now. So
these things that are changing between your 1-year survey and installation, are these licensed services where you would get notice that if something is proposed or about to go in?
Yeah, well, we don't do a good job of keeping up with that as the broadcasters do. I know you can subscribe. I don't know of anything like that for the satellite. We probably should. That might be a good market for somebody. But and sometimes it's just people putting up stuff. We had a facility at a NASA site, and the Navy came in one weekend and put up a terrestrial X-band site on the same frequency that was like 100 feet away, and they come in Monday morning and they want to know, gee, where's all this interference coming from? So they take the antenna and start, looking around, and they blew out every one of the low noise amplifiers. So, I think the Navy kind of thought they could do what they wanted to. I guess they go through a different licensing things, but a lot of these are at military installations. They have different licensings. Even outside the FCC, I don't know what kind of coordination they have, but
yeah, and the cellular, I think they're basically licensed, market wide or nationwide, and they can kind of put stuff where they want because they're causing interference to themselves. But you're out of band and see that interference.
Yeah, another thing too, if you've got, like, we've got people across the street from us, I mean, the spectral density, if it's in the, say, 2.2 to 2.3, for instance, that's only licensed for downlink. That's all you can do. But, if you've got a cell site, and all amplifiers have white noise generation to some degree, it's like with our FM transmitter, we have a mask, but if they don't pay attention to that, it can really raise the noise floor. And, once you do that, you're sunk. There's not anything you can do with it.
Ben says here in the comment, the change from spiral to annular corrugation and helix decreased the connector reliability and intermod generation problem by substantial amounts. And in the West, there are still microflex passive reflectors in use, increased the modulation, decreased reliability.
Okay, that's good information.
Mr. Stewart wants us to know that detailed info on sites is harder to get. We used to all be local users dealing with other local users. Now a team arrives, a turnkey system is dropped into place, and our home team doesn't have the time we had on site. They used to commune with our sites.
We used to know our sites better because it happened slower. And nowadays, the message you get that there's a problem at one of your sites may come from another user coming through saying, by the way, did you know your rack has been stolen? Or your Johnny Stigler will call and say, hey, your 11th harmonic is getting into something in San Angelo.
Don't mess with me.
It wouldn't occur to me. And
No,
once
I
upon a
went.
time, we'd have been a lot farther in front of it.
Yeah, I went to that guy's that you're talking about. I went to his studio and had to talk to him on the phone. I was not impressed. He was not technical. We had
So,
a we had an interference issue in California one time that a friend of mine had installed on top of a mountain, and this was a ski slope, and they had 4 antennas on their 2.4 gigahertz microwave that they were using portable, and it was up there for several years, worked good, and one day it ceased to work, and so I got to investigate that a little bit from several thousand miles away. But it turns out that Verizon had a cell site up there, and they had added some new equipment up there, and it was wiping out the receiver, the LNAs or LNBs on these 4 antennas up there. And I provided all the documentation to the owner of this operation, and Verizon was not aware of this issue, but they ultimately got wind of it and paid all the money to upgrade the receive site system for this non-broadcaster up there, Part 101 user, and the problem went away. But it took about a year to get this solved.
There was talk about imperfect shielding on coax, a gap or something in there. And it reminds me back when using braid shielded coax and double shielded coax and so on, and there was still substantial leakage. Is this solid shield coax? What sort of attenuation is there between inside and outside?
Yeah, we've had pretty good luck with we usually use Heliax, so it's a solid outer conductor. But what I usually try to ask people to do is put the low pass filter for the SSPA next to the SSPA, because the SSPA has a white noise level in the receive band that's enough to degrade your G over T, degrade the signal. So if you can reject that close to the SSPA out to the transmitter output, it's a lot better. Now the problem is they like to put these things up, way maybe 50 feet away, using through a piece of coax. And if you get a break, somebody doesn't know how to install the the connector properly, or it fatigues and breaks. Well, it looks like this Radiax coax that Andrew used to make, that has a break, and then then that white noise that the SSPA is putting out, say in the receive band, it radiates. And once it radiates, if it gets back into the antenna, and these things are awfully sensitive, game's over. There's nothing you can do at that point. I mean, because it's in the same band. You can't receive and reject the same frequencies at the same time. So, that's why it's really important to, sometimes I'll even make these critical connectors myself. Sometimes you have folks that are fairly new to making cables, but you don't want to take your time on that. And if you can, put the low pass filter right at the SSPA output, if it's possible. Because once you reject it, if you have a leakage, it's not that big a deal.
Ray, earlier you mentioned, and several times mentioned, filter early, filter often. Have you, just out of a curiosity point, have you seen any difference in sites with key fobs that filter better than others?
I mean, it's always a balancing act, because I can get a great filter, but if you take this filter and you put it before the initial LNA, the insertion loss of that filter, say if it's 1 dB, that's going to hurt the G over T 2 dB, and people are paying a lot of money for these big antennas, so they don't like that. So usually it's a cascade analysis. You you like these LNAs that have the interstage filters, you'll go up 10, 15 dB, then have the interstage filter, and then you'll do the rest of the amplification, another 30 dB. You come out of the initial LNA, go into another filter. At that point, you've got up 40 dB, so insertion loss is not near as big of a deal, because you say if it's 40 dB, then your whatever the insertion loss is, that noise contributions can be divided by 10,000, say if it's 40 dB, roughly speaking. So you can get a cheaper filter and put it in there, and then you can have a post amplifier that has a 4 or 5 dB noise figure. Like I said, they're a few $100s. They can be a half a watt. So it's just trying to. I don't know that you want to do it all at one place, because the idea is it's a balancing act between G over T, preserving the G over T, and the noise mitigation. But I like to do it a little bit at a time if you can. So. And
I guess I'm asking sort of a side point or a trivial point, but do you find some sites where key fobs work?
What is key fob now? I'm sorry. What's that's
For your car. Now, if I go up here to Tucson Mountain,
oh,
as
okay.
an
I'm sorry
example,
for that. Okay.
I can't open my car door with a key fob.
Okay, I've got an old car, so.
And
no, I've never seen
probably-
that, but I've got an old timey car, so it's
you probably remember that when they started with these things, that there was a zone right around the Empire State Building that people were towing their cars every day because they couldn't get back into them.
back in it.
Yeah.
No, okay, I hadn't heard that. Wow, I can see how that would happen. There's
So
not
I
a
was
lot
just
of room
wondering-
in one of these for a filter, so so.
Just
Even
wondering
worse
if-
with pacemakers.
Yeah, I have the problem every once in a while at Tampa Airport where the key fob won't work.
So that's probably just receiver overload rather than interference, I suspect.
Both.
Yeah, it could be both, but yeah, they're pretty cheap receivers.
Built in a little plastic doodad that'll fit on the keychain. So it's not very big, and it's certainly not very shielded.
Yeah, of course, the receivers
Those
in
are
the car.
transmitters. Those aren't the receivers, David.
True enough, yeah. But
The
even
receivers are
Yep. But even there, you can only shield it to a counterpoise, not to really a ground. And
We used to go out to dinner out at Cedar Hill, and we'd have problem over at the Cotton Patch. We couldn't open any of our vehicles. Well, we learned which fender well and where to hold the key fob that would open your vehicle.
last time we went with Jack to the Cotton Patch, the problem wasn't the key fob, it was the menu.
I
think we ended up
understand
in a
that comment.
McAllister's Deli.
Yeah, I understand.
No real Coke and no grilled cheese sandwiches. Let's get out of here.
And we got up and we left.
Yes, we did.
It cost us 2 stops of the itinerary, but he got his cheese sandwich.
Oh, wait, we got to go back and get Jack. On the way.
Well,
Lots
Ray,
of stories there.
Ray, I think really appreciate your taking the time to share this information with us and walk us through what can be going on up there. And there's so many other things, transmitters. I mentioned, I think, the LTE debacle a few years ago with FM at the 8th or 9th harmonic, and you can have a problem because leakage from the exciter through the transmitter door sometimes will set off these cell sites that we're trying to be very, very, very quiet. So it helps us all appreciate the value of study, filter, and paying attention to what the other guy's doing.
I think one of the funniest things I ever saw happen, we used to do a lot, we had a radar division and I worked in that for quite a while, and they were on site at a military installation testing a radar, and they had a new base commander come on, and he didn't like the fact that in the hangar they had fluorescent lights with blue tinge lights and others are pink, and he said, I don't know, I don't care, I want them all the same. So this poor janitor had been replacing fluorescent lights all day long, and it was 7 o'clock, everybody was tired. he walked too close to our radar that they were testing. I think it was like 1.5 megawatts. Every one of these light bulbs in his hand lit up. He took every one of them and threw it, and it was, nobody got hurt, but it was a mess. So I never will forget that. So that was kind of funny. Funny now, wasn't so funny back then.
So again, it's impressive the frequencies and noise levels you're working with. Very impressed. So thank you for the presentation.
Thank you. Well, I enjoy being with you guys. I'm trying to get back into broadcasting the past 6 or 7 years, and it gets in your blood and you don't want to leave it. That's for sure.